This video we're going to talk about prepare standard solution, and the method that we're using this time is dissolving pure solid. Before we talk about how to prepare standard solutions, first of all, you have to note the characteristics of primary standard. First of all, you have to know that they have to be readily available. That means easy to obtain. And also they should have a very high purity. That means it shouldn't have other kinds of impurities in it. And for the chemical, it have to be chemically stable, not going to react with oxygen, carbon dioxide, and water, which easily access in the air. If they react quite often, then even we measure the primary standard, okay, it may eventually turn into other kind of substance. Then the solutions that we prepare will not be pure. And because we are going to dissolve the chemicals in the water, so it have to be highly soluble in water, but at the same time, okay, it should not be absorb water vapor in air. That means it is not hygroscopic. Okay, these words, okay, you have to pay attention to that. Not hygroscopic. Okay, because if it is hygroscopic, okay, say for example, okay, I put the chemicals on the electron balance, it tells you that 10 gram, but this 10 gram, it may be because it have like 9.5 gram of the chemical, it may still have 0.5 gram of water if it is hygroscopic. I don't want to have these situations happen, so therefore the chemical have not should not be easily absorb water vapor in the air. This one, okay, is different from chemically stable because absorbing water vapor, it doesn't mean that it have reaction with the water, oxygen, or carbon dioxide. So therefore, I'll separate this one in 2 points. And point 5, it have to be involatile. Involatile, that means that it not vaporize easily. If some chemical, say for example, I have a solution, it say that it is 2M or say for example 2MNH3. So if I put it there for a few days, okay, if it have the water or ammonia, it vaporize, then maybe the concentration it will change to, say for example, 1.95 m. So in this case, okay, we can't tell, okay, the concentrations of it accurately, then it should not be used as a primary standard. Finally, okay, the chemical should not be toxic. Okay, we have to be safe to use it. According to the criteria listed in the previous slide, some of the chemicals are listed not a good examples, okay, commonly see in the public exam as well. So the first one would be sodium hydroxide. Sodium hydroxide, you have to know that it is hygroscopic. That means it will absorb moisture in the air. So just now we have mentioned, if we absorb the moisture in the air, the mass of NaOH will not be accurately measured because some of them they may include water as well. Not only this, okay, not only it is hygroscopic, but also NaOH can react with the carbon dioxide. As you know that sodium hydroxide is alkaline, and then carbon dioxide is acidic gas. So therefore, it may react with the carbon dioxide, so it have neutralization. So the amount of sodium hydroxide we obtain will be less than expected. While for the H2SO4 Conc hydrochloric acid, Conc sulfuric acid, it is hygroscopic. Okay, it will be easily absorb moisture in the air. So by doing this, okay, we'll find that the molarity listed, it will be larger than the actual molarity. Because of the molarity, it will going down because it absorbs water, it will be diluted in the process. Okay, absorb water and then it will be diluted. Okay, so the molarity, it will go down. And for ammonia, okay, not only it is toxic, okay, it have a pungent smell, it is toxic, but at the same time we can smell that because it is volatile. So therefore the molarity, it is also inaccurate as well. Okay, volatile, that means the NH3 will leave the solutions and get into the atmospheres. Okay. So in your textbook, okay, example 19.1, okay, it will be a good exercise. Okay, you see that, okay, sodium hydroxide pellets means solid. Okay, it's just like a pills. Okay, so this one will absorb water vapor from the air and dissolve in it, and making the mass of the pellet difficult to measure accurately. These will be the key words. Okay, not only that, they will react with the carbon dioxide. Conc of reacted, they will absorb water vapor from the air, so therefore the concentration inaccurate. Okay, this one is volatile. Okay, so therefore in the process, okay, the concentration will be inaccurate as well. So two ways to prepare a standard solution. Remember, standard solution means that the molarity is accurately known. Okay, so we have to know the molarity of the solutions accurately. There is two ways to do that. The first one is by dissolving a pure solid. If you refer to the equation, molarity equals to number of mole over volume. Okay, and number of mole can consider as mass over molar mass over volume. Okay, so as long as if we know the mass accurately, we can do this easily by electronic balance. And molar mass, this one must be fixed because you find this in the periodic table. And then the volume, okay, if we have a accurately known mass, we know the number of mole, and we dissolve this mass into a fixed volume of solutions, then we can make a solutions with an accurately known molarity because we know these two parameters accurately. So the volume, okay, that we're talking about, it will be talking about the volumetric flask. Okay, so immersions, okay, we got a volumetric flask. We know that this is 250.0 cm cube. The volume is accurately known. Okay, and then we got an electronic balance, and then we can weight the chemical accurately. Say, for example, this is 10.0 gram. So by doing so, okay, we can make a solutions with accurately known molarity. The second way that we can do, okay, is by diluting a concentrated solutions of a known molarity. Again, okay, if we want to find the molarity of M2, okay, if we know the M1, say for example, we know the molarity of the original solution. If we buy it from a chemical store, they will tell you the molarity accurately. Say for example, the stock solution. Stock solution, that means we buy it from the chemical store, we put it in the stock. Okay, say for example, it is 10 m. Okay, and if we measure the original volume, say for example, we use a pipette. We use a pipette to measure exact volume 25.0 cm cube, and we put it again in a volumetric flask, say for example 250 cm cube. So we have this one, okay, the V2 referring to the V flask, or V1 referred to the pipette. Okay, if we have this one accurately known, and accurately known, then we can calculate a very accurate molarity by doing so. So in this video, first of all, we're going to talk about the first method by dissolving a mass, okay, into a known volume of solutions. So say for example, if we want to prepare 250 cm cube of 0.1 m sodium carbonate solution. You see it right now, we use the terms approximately. Approximately because right now we're going to dissolve some sodium carbonate solid into the water, and the water is 250 cm cube. If we want to make exactly 0.1 m, then when we measure the mass, okay, it have to be very, very accurate. Okay, let me do it the calculation to show you, okay, what means by that. Say for example, okay, the chemical right now that we're using is anhydrous sodium carbonate solid. Okay, so if we want to prepare 0.1 m 250 cm cube solutions, how much solid do we need? Okay, so first of all, okay, we have to calculate the number of mole that we need. Okay, the number of mole of Na2CO3. Okay, the one that we need to use is M times V. So we have 0.1 times 0.25. Okay, this one is the dm cube. Okay, so by doing so, we know that we need a 0.025 mole. Okay, Na2CO3. Okay, then how much mass of Na2CO3 do we need then? Well, the mass of Na2CO3 would then be 0.025 because mass equals to number of mole times molar mass. okay? So therefore, we're going to times 23 times 2 plus 12 plus 16 times 3, okay? So therefore, this one will be equals to 106, and it will equals to 2.65 gram. Okay, now we know that if we want to prepare these solutions, we need 2.65 gram. But when you go to lab, okay, when you try to measure 2.65 gram, actually every time it won't be that exactly. Maybe you got like 2.73 gram. So at this moment, do you need to like remove the extra 0.08 gram? The answer is no need, okay? Why it have to be like that, okay? Because standard solutions, the key point is accurately known molarity. It is not necessary to be this exact 0.10 m. So if you have 2.73 gram right now, which is very close to 2.65 gram, actually it is okay, because at the end you need to use this data 2.73 gram, then you're going to convert into a molarity. Say for example 2.73 over 106, and then you have 0.25. By doing so, okay, you can calculate the molarity of it, and this one will be 0.103 molar. So you'll find that this molarity will be referring to your standard solution, and this one will be so close to 0.10 m, and it is acceptable. So you will find that when you do the experiments, actually what you're preparing the standard solutions will be different from your classmates, okay, sitting next to you, because maybe your mass will be slightly higher than 2.65, while the others may be slightly lower than that, okay? So everyone, the standard solutions will be different by doing so. So the procedures, okay, basically, okay, what you need to do, first of all, you have to calculate the mass required. Okay, you have to calculate the mass required. So in this case, we need 2.65 gram. Okay, but when we weigh out the mass required, everyone will be slightly different. Okay, so your concentrations, the molarity of your sand solutions will be different. After you do this, okay, we're going to pour it in a beaker, and then we'll try to dissolve it in the water. Even we're going to prepare 250 cm cube, we are not doing that directly. Okay, we have to use around 100 cm cube to dissolve this chemical first. After we dissolve the sodium carbonate, we'll pour it into a volumetric flask. Okay, we'll transfer to 250 cm cube volumetric flask. Okay, this volume and also this name is very, very important. After doing so, okay, you'll find that the beaker itself, you may still have some sodium carbonate solution liquid, okay, high on the wall. Okay, so right now, okay, what you need to do, okay, you add some distilled water to rinse it. Okay, you have to wash the beaker and then pour all the washing, because this washing, okay, it may contain sodium carbonate here. Okay, so therefore you need to pour all these solutions back into the sodium carbonate, back into the volumetric flask as well. Okay, I say reflask, okay, to save some spacing. Okay, you have to repeat this washing and pouring all washings, okay, at least 2 to 3 times. Okay, but when you write, okay, you don't need to write that details. You just tell them that wash the beaker and pour all the washings to a volumetric flask will do. You imagine, because if we at the beginning, okay, we use 100 cm cube, but if you use 250 cm cube at the very beginning, then it won't be able, okay, for you to add extra washing into the volumetric flask anymore. Okay, so each washing, it may carry about 20 cm cube of solutions. So you can see that, okay, if 20 cm cube each time, you need to do 3 more times. This may up to 60 cm cube. If at the beginning you use a large amount of volume, okay, of water to dissolve the sodium carbonate, then at that time you will be more than 250 cm cube. Get it? So at the end, okay, what you need to do after you do all the washing, transfer all the washing in volumetric flask, you add distilled water. Okay, key points come here. Until the bottom of meniscus reach the graduation mark. If you remember, this is called graduation mark, and the water level, okay, you will see a meniscus. It is not a straight line, it is a curvatures. Okay, we want to have the bottom of the curvatures touch this graduation mark. If it touch this graduation mark, that means the volume of water inside of solutions inside this volumetric flask will exactly weigh 250 cm cube, okay, in this case. Okay, so this is what you have to write. This is the most important statement. And afterward, okay, you just need to stop the flask, and then you mix it well. It will be done. So procedures, okay, written format. Okay, remember this is essay type question. So key things, okay, no point form, and also have to be complete sentence. Okay, so I've highlighted the keywords, okay, for you. So when you revise, you don't need to statement by statement. You just remember the keywords will do. So first of all, calculate the mass, okay, and you have to show the steps most of the times, okay, and then use electron balance to weigh, dissolve the solid, transfer it to 250 cm cube volumetric flask, okay. Wash the beaker, pour all the washing, and then add distilled water until the bottom of meniscus reach the graduation mark. Okay, so this one have to be word by word. Okay, very important statement. Okay, and finally you stop it and mix it well. Okay, so right here, okay, I have got you a QR code to show you how to prepare a standard solution. So basically, okay, you can see example 19.2 to show you, you can do a math, okay, to tell you how to what is the molarity of the solutions. So say for example, right now this time we have used 3.20 gram of Na2CO3. This is anhydrous, that means no water in it. So the number of mole of Na2CO3 will then be 3.20 over 23 times 2 plus 12 plus 16 times 3, which will then equals to 0.030 number of mole. Okay, so you may write 3 sig fig for it. Okay, 302, because right now in the early stage shouldn't run up too early. And afterward, okay, the molarity will then equal to 0.0302 over 250 over 1000. Remember in dm cube. So this one, okay, 0.0302 divided by 0.25. Okay, so this one will be equals to 0.121 molar. Okay, so that will be how we do. Okay, at the end, okay, you have to use the mass that you weighed by the electronic balance and do the following steps to find out the molarity of your standard solution. Remember, everyone's standard solutions will be different, so their titration result will also be different. Say for example, student A, they use 20 cm cube, while student B, they not necessary to be 20 cm cube, they may be 20.5 cm cube. Okay, so that will be how we're going to prepare standard solution. To summarize the videos, okay, you have to remember standard solutions, okay, is a solutions with accurately known molarity. The criteria to be a primary standard, okay, will be as follow. Most important, okay, have to be chemically stable, involatile, does not absorb moisture in the air. Okay, and common bad example of primary standard, you have NaOH, hygroscopic, and reaction with carbon dioxide. Conc H2SO4, it is also hygroscopic. Ammonia, which is volatiles, and also it is toxic. Okay, so these are not commonly used as primary standard. The one that we use, okay, commonly mentioned is sodium carbonate. Okay, the procedures to prepare standard solutions. This is what I recommend you remember the keywords of each steps. Okay, so say for example, you have to calculate, you have to weigh it, dissolve it in volumetric flask, washing. All these words are very important in working out the essays. Okay, and at the end, okay, you have to calculate the molarity of your standard solutions. Okay, so that's all for this video. Bye bye.